Good morning, good afternoon, and good evening. Welcome to the Crazy Hat Chemist. And here we are, folks. We are going to do a lab of which I've designed. It's called the Lewis Structure Model Lab. This is a dry lab in my honors chemistry class. So what do you need to do this lab? Well, you need the following. You need one, the lab that you see before you, and of course, you need this right here. This right here gives you an idea of what we're doing. This is a covalent bonding handout that I have. There, if you go to my honors chemistry, the bonding collection and bonding video number 28 on molecular geometry, it explains what all this means. What does all this mean? It talks about VSEPR theory. Furthermore, we're going to flip this over. And right here, Honors Chemistry 6, the bonding collection, bonding 11, Lewis dot structure rules. So these are the rules for Lewis dot structures. And I am going to be following this set of rules in order to do all these problems. Some things that will be covered in here are resonance structures and geometric isomer structures as well. Okay. All right. So that's one thing that you need. You need to keep it handy so that you can understand what's going on. And you also need a periodic table. So with that periodic table, we're going to do a few things. What we're going to do is we're going to get rid of all those F grades. Those are the F-type orbitals. So we're going to take our periodic table. We're going to fold out the Fs. The other grade we don't want are Ds. So we're going to get rid of the Ds as well. You know, I wish I could do this this simply with my students and just fold them out, right? As far as their D grades, that would be so nicely. Not those students, not at all. Has nothing to do with the students, just the grades of Ds. Hopefully you understand that. Okay. And then we're going to keep on folding this. And what do we end up having right here? So right here is what we have. And we're going to write in a Sharpie here. There we go. We're going to write the number of valence electrons. So this is 1, 2, 3, 4, 5, 6, 7, and 8, excluding helium. Helium doesn't form any compounds, so I'm not really worried about that anyway. But in these columns, these are groups, vertical columns. Those are the number of valence electrons. And I'll be referring to that frequently throughout this video, and hopefully you get that. All right. All right, so you got that periodic table. You got my set of rules, covalent bonding handout. And if you're looking for that, maybe you can shoot me an email and, maybe I'll email you a copy of this. That would be a good idea. And on the backside is the Lewis structure rules, okay? And also we got resonance and geometric isomers. By the way, just a quick little advertisement here. Since you are here, I am the Crazy Hat Chemist, and I'm here for all your chemistry needs that are true and correct as far as the learning experience in chemistry goes. All right. So without further ado, let's keep on going here on this and let's move forward. So we're going to do each one of these problems here, and we're going to do them in a particular order. Okay, so what we're going to do is fill out this. Where there are X's, that means nothing, that means it's not applicable. So there will be some here towards the end that will have a blank spot that you can put something in. All right, so here we go. So like I said, we're going to be using that periodic table, and we're going to first count up the number of valence electrons. So we're going to zoom in on this here just a little bit so that we see the necessary portions here of this worksheet here. And I believe we are almost there. There we go. We're just about there. Here we go. All right. So this is really what we're looking at here. And we want to fill out this table here. Made a little bit larger so that you can actually see it. So the first thing that we're going to do is we're going to use our periodic table, like what we have folded out, the Ds and the Fs, and we're going to count up the total number of valence electrons. And I am actually following this set of rules here. You want to follow these set of rules in this order to the T, and it will make more sense that way. All right. Okay. Whew. Let's see if we can try this again here. Here's carbon, and it has 4 valence electrons. And then what we're going to do is how many carbon atoms are there? There's 1 carbon atom in this. And then we are going to add that to the number of valence electrons for hydrogen, which is 1, but there are 4 hydrogens in this. And so we're going to do that math right there. That is 8. So the total number of valence electrons is 8. But I am not going to just do the number of valence electrons. I am going to work in pairs because the crazy hat chemist can't count very well. So we're going to work in pairs. That will be much faster to work in pairs than just the total number of electrons. That's not the right way to do it here. So we're going to take that crazy 8 there, divide by 2, and then we're going to have 4 pairs. So this is going to be pairs of electrons in this column here, if you will. And again, we're following the rules. The least electronegative element goes in the middle, but never hydrogen. That's the rule. And then from a previous unit, you should understand that fluorine is the most electronegative element. So what we're doing is we're trying to find the element that is furthest from fluorine, but never hydrogen. Hydrogen cannot branch off, and that's why it is never the central element. So what we're going to have is carbon in the middle, just like that. And then we're going to follow like the sign of the cross or a plus sign or the faces of a clock. And that is 3 o'clock, 6 o'clock, 9 o'clock, and 12 o'clock. Okay. And then from there, then the next rule is to place a pair of bonding electrons between the central and the outside element. Central, outside element, that's 1, that's 2, that's 3, that's 4 bonding pairs of electrons. Okay, and then the next thing that you do is you need to verify the octet and duet rules. The octet rule applies to all elements, and so I'm going to take like this, and we don't actually write this on here, so that's why I'm going to do it in pencil. Is there an octet around that carbon? Because there are 4 elements which must have an octet, and those are the only 4 elements that must have an octet. And those 4 elements are right here in this rectangular box. These 4 elements, that is carbon, nitrogen, oxygen, and fluorine, must have an octet, period, end of story. Okay, and so is there an octet around that carbon? Because it must have an octet. That's 2, 4, 6, 8. Yes, it does. I'm going to circle this hydrogen. Does it have a duet? Yes, it does. That's a duet. That's 2 is a duet. Does this hydrogen have a duet? Yes, it does. That's a duet. Does this hydrogen have a duet? Yes, it does. And does this hydrogen have a duet? Oh, most certainly. Now, those circlings are really not part of what we want on a Lewis dot structure. You actually do that just in your mind. So what I'm going to do is I'm going to take an eraser and erase all that because that's really not supposed to be there. That doesn't belong, in other words. So that's what we should have. All right. Now, the next column here is the VSEPR geometry. So we need to work on the VSEPR geometry. And again, this is coming from my handout. If you need this, shoot me an email or in the comments and I'll send this to you. Okay, so the VSEPR geometry is following what we call, or I call the axe. The axe, the A on the axe is the central element. The X are the outside elements that are attached to the central element. And the E are the lone pair of electrons attached to the central element only. So axe, the A is the carbon. The X are the elements that are attached to carbon. So that's 1, 2, 3, and 4 of them. Are there any lone pairs on the central element? That is absolutely not. So AX4 corresponds to a name of a shape. So this is actually not the answer here. Okay, this gets you to the answer. The answer is the name of the shape. So what's the name of the shape associated with AX4? That's tetrahedral. This is horizontally located here, AX4 and tetrahedral. That's why this sheet of paper is so important. All right, fantastic. So now we have tetrahedral. Beautiful. Now, the next column here is hybridization. Hybridization, we are just going to name the hybridization, get the naming correct here. All right, and that's our goal here is get the naming of the hybridization. All it is a numbering system of the number of domains around the central element. That is the number of domains around the central element. So we're going to count them. That is 1, 2, 3, and 4. But how we count those is not just with numbers. We count them as S, P1, P2, P3. So we're going to count S, P1, P2, P3. And then we fuse that all together because it's actually a hybrid. So that's going to be sp3 hybridized. So let me erase that right over here because again, that does not actually belong here. And when we are counting this hybridization, it's actually S, P1, P2, P3, D1, and D2. Okay, so that's our order. That means that there's 1, 2, 3, 4, 5, and 6 potential domains or regions around the central atom. That's what we're looking for. Our next column here is called bond angles. Oh, by the way, if you want to know more about what hybridization means and what it actually means, besides just counting it up and determining its value, if you will, its nomenclature of sp3, then you really need to be watching some of my advanced placement chemistry videos, and that would be a bonding collection in that. And that's in that bonding collection. It talks about why hybridization, what's important about that VSEPR bond theory, and why hybridization is important for the valence bond theory. It's a correction factor. The next thing that we're going to do is the bond angle. And the bond angle is associated with the VSEPR shape. By the way, VSEPR means valence shell electron pair repulsion. And I do have that on this handout, on this worksheet. It does specifically talk about the VSEPR theory, what it is, what the axe is, everything right there. Again, if you need one of these, shoot me an email. I'll send it to you. Bond angle. So bond angles for tetrahedral is the following. So if it is AX4, that's tetrahedral, and the bond angle is 109.5. Okay. So that is a bond angle of 109.5 degrees. All right, now at this point in time, you are supposed to have a model kit. And with that model kit, you are supposed to build the model. So I've built the model here for you, and here it is. I'm going to turn this just a little bit so you can actually see it. This is a tetrahedral arrangement of all these. The black things are representing carbon. The white things are representing hydrogen, and the gray things are representing pairs of electrons bonded together. Okay, so this is tetrahedral. Tetra is the prefix for 4, so that's why there are 4 domains around this, all bonding domains. So now this next column is called molecular polarity. So molecular polarity follows 2 essential little rules, and those rules here, I'm just going to write them down. Polar. Is it polar? Number 1. In order for it to be polar, you must have polar bonds. Does it have polar bonds? Are you going to put a check in here? Okay. Number 2, asymmetrical. Is it asymmetrical? Are you going to put a check in this box? Remember, it's asymmetrical. So if you put a check in both of these boxes, then yes, it is polar. If one of these boxes is unchecked, it is not polar. Okay. So first of all, is there a difference in electronegativity between the carbon and the hydrogen? There is a difference in electronegativity, not very much of a difference. It's a very, very slight difference. Okay. It's almost a covalent bond, partially polar, but let's actually look at this shape. This shape is tetrahedral, and all these white things are exactly the same. So really what it is carbon has more electronegativity than does hydrogen. So the bond polarity is going towards this carbon. And then this bond polarity goes towards the carbon, this bond polarity goes towards the carbon, and this bond polarity goes towards the carbon. So that means that all the bond polarities are pointing inward into that carbon, and that is actually symmetrical. And so because it's symmetrical, this is going to be non-polar here for methane. By the way, this is methane. It is the simplest hydrocarbon. All right, so we're going to do more of those, and let's see if we can answer any questions as we continue on with that. So our next one here is ammonia. And ammonia is NH3 that has 5 valence electrons. This has 1 valence electron. There are three hydrogens, and there's one nitrogen. That's a total of 8 electrons. I'm going to divide by 2. I'm going to get 4 pairs. The least electronegative element goes in the middle, but never hydrogen. Consequently, what goes in the middle? Nitrogen goes in the middle. Then I'm going to place those hydrogens around it like such, like 3 o'clock, 6 o'clock, 9 o'clock. I've ran out of hydrogens to be placing around them. The next rule is to place bonding pairs of electrons between the central element, that's the nitrogen on the outside element, central element outside, central element outside. Okay. The next rule is to place lone pairs of electrons on the outside elements. And so I've got 2 more electrons, boom, boom, boom. So there are many students that do this. However, this is completely incorrect. Okay, and why is this incorrect? And that is because I'm going to circle this hydrogen, and notice that this hydrogen is not following the duet rule anymore. This has greater than a duet, and hydrogen, like this hydrogen, follows the duet rule. That is the rule for hydrogen. It must follow the duet rule. So this is a violation of the duet rule of this hydrogen. So there is never a possibility that you have a lone pair of electrons on hydrogen. There's never a possibility that you have a double bond on a hydrogen. Those will be always violations of the duet rule. So we're going to erase that because those don't belong there. The next rule is to place lone pairs of electrons on the central element. And that's what we're going to do right here. So now we've placed those lone pairs of electrons around the central element on the nitrogen, and that is correct. We're going to get the VSEPR geometry from this, and that central element is the A, and that's the nitrogen, and then the outside elements physically attached to the nitrogen are hydrogens, and there are 3 of those. Then there is a lone pair. I'll just loop that over there. That is an E on the central element. And again, I'm using this table here to come up with what is the name of that, and that is AX3E, that is trigonal or trigonal pyramidal. So that is trigonal pyramidal. Okay, and in regards to the bond angle, we can get the bond angle directly from trigonal pyramidal, and that is 107 degrees. Okay, there's a really interesting issue between the methane and the ammonia and the bond angles. Okay, the hybridization, I'm going to count the regions or domains around the central atom, and that is 1, 2, 3, and 4. So that's S, P1, P2, P3. That lone pairs is still a domain around the central atom. So that's 4 domains, S, P1, P2, P3. So this is sp3 hybridized, okay? So we have, you're going to make a model from your model kit, and this is ammonia. So let me tilt this just slightly so you can see this here. So the blue thing in the middle is representing that nitrogen. The white things are representing the hydrogens. The gray things are the bonding pair of electrons in between the hydrogen and the nitrogen. And that little tan thing on top, that is the lone pair on the central atom. Now you should see that this molecule here is not completely flat. That is, the hydrogens and the nitrogen are not in the same plane. That makes this trigonal or trigonal, 1, 2, 3 hydrogens, pyramidal. So this is pyramidal in shape. Does this have bond polarity? Yes, it does. So we're looking whether or not this is polar or non-polar. So the nitrogen is more electronegative than the hydrogen. So the bond polarity goes in this direction, and this direction. And then this lone pair of electrons also goes in this direction. So the bond polarity ultimately is like a giant arrow pointing right through that nitrogen and right through that lone pair of electrons. So if you can draw that molecular dipole, that means it's a polar molecule. In fact, anything that is trigonal pyramidal, AX3E, is polar. All right. Next one is going to be water. So that is one valence electron, of which there are two of those hydrogens, and six valence electrons, of which there is one. I'm going to add those up. That's 8. I'm going to divide by 2. I'm going to get 4 pair. The least electronegative element goes in the middle, but never hydrogen. That's the oxygen. And then I got a hydrogen here and a hydrogen here. I'm going to follow my rules again. Bonding pairs of electrons between the central and outside, and then lone pairs on the outside elements. And we have already discovered that we cannot do that. So we are going to bypass that rule of putting lone pairs on the outside atoms. And now we're going to dump the remaining bit of electrons on the center atom. Okay. This is now A for that oxygen, X for the atoms that are attached to the oxygen. There are two of them. And E for the lone pair of electrons, of which there's 1 and 2 pairs. So that's AX2E2. This is bent or angular. Okay, bent or angular has a bond angle of 105. Again, this is coming directly from my table. I highly recommend that you memorize certain sections of this table. What 3 columns would one memorize? You should memorize the X, the molecular geometry, and the bond angle. Okay, the polarity and the hybridization, you should be able to derive that. And the columns on the left-hand side, the central domains, the bonding domains, and the non-bonding domains are things that you can derive, as well as the molecular polarity and the hybridization. Okay. All right. Now we're going to get the hybridization. That's S, P1, P2, P3. Again, that's S, P1, P2, P3. So this is sp3 hybridized. Okay. Then you're going to get your model kit and you're going to build water. And here is water. The red thing in the middle, that's the oxygen. Again, the two white things are hydrogens. The gray things are bonding pairs. And these tan things are lone pairs of electrons. And this is water. Okay. Just going to turn this around here just a little bit so you can see it in all its three-dimensionality, hopefully. Yep. This has bond polarity. That is, the oxygen is much more electronegative than the hydrogen, and that arrow goes in that direction. This bond polarity goes in that direction. Then there's bond, not really a bond polarity, but there's these lone pairs of electrons. And so overall, there's a net molecular dipole that's coming out of here like this. That means if it has a molecular dipole, it's polar. I want you to pay attention to something really, really important because this is always a question on any chemistry exam, and they are comparing these 3 molecules. They are all sp3 hybridized, and their polarity is not the issue right now. What is the issue is that they are all sp3 hybridized. That means all 3 of these have 4 domains on them. How they really actually differ is with their bonding angles. Okay, so that is this bonding angle is different than this bonding angle, which is different than this bonding angle. And why are the angles different, even though they are all sp3 hybridized? The reason that these bonding angles are different is because the increasing number of lone pairs. No lone pairs, the bonding angle is 109.5. At 1 lone pair, there's a compression of this bond angle. Instead of 109.5, it's 107. If you have 2 lone pairs on that central atom, there's further compression of this bond angle, and now it's 105. So it's about 2 degrees difference each time that you add a lone pair of electrons on a tetrahedral arrangement of electron domains. It's really important that you know that. All right, so one other thing that I'm going to mention and draw out, and what I see very frequently for students is drawing out the Lewis dot structure for water as the following. And I'm going to do it a little bit smaller, but it doesn't matter. So you can draw it like this, here and here, here and here. And this is a perfectly acceptable Lewis dot structure. There is nothing wrong with that Lewis dot structure. But this leads to the false idea that it is linear. It is certainly not linear. This is why it's essential that you build the molecules itself with a molecule kit. Hopefully you can get a hold of one from your chemistry teacher or professor. Also, if you follow the axe, That's A, X2, E1, E2. You understand that this is angular or bent and not linear. All right, very important. These are three most important molecules. They are covered in every single chemistry textbook. All right, let's move on to the next one here for you. Okay, the next one here is nitrogen, and this is molecular nitrogen. I'm going to zoom on out just slightly so that we can have this entire sheet of paper there with all the parts. Yes, there we go. So nitrogen has 5 valence electrons. There happens to be 2 of them here. And so there are 10 total electrons. Divide by 2, and that will give me 5 pair. I have a nitrogen and a nitrogen. One of the most common mistakes is just to draw one of these nitrogens. There's actually 2 right there. Don't forget about that. It's actually, look at that. There's 2. That's why you have 10 total electrons. Okay, so here we go. First is we're going to put a bond in the middle. So 1, 2, 3, 4, 5. 5 pairs. So now what we do is we circle these, and we don't actually physically circle these, right? Hopefully you understand you're doing this in your mind's head here, or your mind's mind, if you will. And so the nitrogen on the right-hand side has 2, 4, 6, 8 electrons, and this nitrogen on the left-hand side has 2 and 4. And so this nitrogen on the left-hand side needs an octet. That is, nitrogen is one of the 4 elements which must have an octet. So what you're going to do is erase a pair of electrons right here, and sharing is caring. So we're going to place a pair of electrons in between. You're still keeping them within the circle of this nitrogen on the right because it had an octet. You're going to keep an octet. Okay, but this is a double bond. Okay, and well, this nitrogen has now 6 electrons. It had 4, but now it still needs more. So now what we're going to do is we're going to erase this pair of electrons, and we're going to put it right over here, and that is a triple bond. Perfect. So I'm going to erase everything here and then get your final answer here, and that would be something like this. The lone pairs of electrons don't need to be exactly opposite, but that is actually how the molecule is. In terms of its VSEPR geometry, you cannot do a VSEPR shape because there is not 3 elements. You need 3 elements for a shape. So we're going to say no shape. Some people might say that it's linear, and they are not necessarily incorrect either, but that's not under the highlights of this category. But it does have hybridization. That's SP. It's SP hybridize. Since it has no shape, it would have no bond angle. So this is Na, if you will. And there's no difference in electronegativity. They're the same element, so your change or difference in electronegativity is nothing. So therefore, it fails on this first category of polarity, right? Are there polar bonds? That's a no. We don't even have to look at the symmetry of it, even though it is symmetrical. So this is non-polar. And what does this look like? It looks like that right there. That is a triple bond, okay? And these are the 2 nitrogens, and these 2 pink things are the lone pairs of electrons sticking out. And you can see why some people might call this linear, and they might not necessarily be incorrect. But for us, we're going to say that it has no shape, all right? Cool. All right, fantastic. So that is the front sheet of my lab right here. And yes, by the way, we are watching videos here on the Crazy Hat Chemist. So we're going to flip this lab over. We're going to do the next problem here. So let's find the next problem to do on the flip side of that. And let's see what we can do here. So we're going to be doing the same thing here that we did on the previous one. I'm going to zoom in on here just a little bit so we can get just all the parts to these problems here. So you can see it as large as possible. All right, we are almost there. Apologize for the little disruption there. All right, cool. Put a few weights on here. Remember, you are watching the Crazy Hat Chemist. Don't forget about that. Don't forget to like and subscribe. All right, so here we go. This next one here is SO4. The name of this is sulfate. Okay, that's one of those polyatomic ions that you should be memorizing in your polyatomic ions, if you will. Okay, so sulfur has 6 valence electrons. There is one of those. Oxygen has 6 valence electrons. There's 4 of those. Sorry, that's in the wrong color, 4. And then we have this 2 minus. Now we are counting up electrons, and electrons are what charge? They are negative. So we are going to add 2. We're going to add for however many charges we have. So since we have a 2 minus charge, we're going to add 2. So that means that we have a total of 32 electrons. And remember, the crazy hat chemist can't actually count, so we're going to divide by 2, and that will be 16 pair. Okay, perfect. Got that. All right. Now what we need to do is we need to figure out the least electronegative element, and that is going to go in the middle. So what I tell my students is to do the following. Okay. Right now I am choosing between oxygen and sulfur. And so it looks like they're equal distant away from fluorine. But what I do is I put a dot in the center of fluorine and then draw a line to the element that I'm looking for. And I put a dot in the center of fluorine and the dot in the center of the element that I'm looking for. And then I compare the length of line. The longer the line, that is the least electronegative element. So sulfur has a longer line than the oxygen does. So therefore, the sulfur is going to go in the middle. So I'm going to have the sulfur in the middle. Then I'm going to have the oxygens around it, 3 o'clock, 6 o'clock, 9 o'clock, and 12 o'clock. Then my next rule is to place bonding pairs of electrons between the central and outside, central and outside, central and outside, central and outside. I have used 4 of my 16 pair. My next rule is to place lone pairs on the outside elements. So that's 4, 5, 6, 7 total pairs, 8, 9, 10, 11, 12, 13, 14, 15, and finally 16. Perfect. So this has 16 pairs. Remember what we do is we circle these and we verify the octet rule. The octet rule is satisfied for this 3 o'clock oxygen. The octet rule is satisfied for this 6 o'clock oxygen. And this octet rule is satisfied for this 9 o'clock oxygen. And the octet rule is satisfied for this 12 o'clock oxygen. Because this is an ion, what we need to do is we need to put this in brackets like this, and we need to put the charge of that ion in the upper right-hand corner, just as it was right there. Perfect. That looks great. All right, so our next column here is the VSEPR geometry, and that is A for that sulfur, X for each of the oxygens, of which there are 4. There are no lone pairs on that central atom, so this is tetrahedral. And consequently, the bond angle is 109.5 degrees, being that it is tetrahedral. Hybridization, remember, it's sp1, p2, p3. This is sp3 hybridized. sp3 hybridized. The molecular polarity. So you got to build the molecule, and it effectively looks just like this. Any tetrahedral is going to look really the same thing. This case here, in this particular case, we're assuming that that sulfur is the black thing and the oxygens are the white things. Even that's incorrect, but it does have polar bonds, but it is symmetrical, so this is non-polar. Perfect. All right, we're going to do the next one here, and this one here is also this is a charged molecule. It's not an ion. This is called the hydronium ion. And when you get to acid-base chemistry, this is going to be oh so most important. That is 1 valence electron, of which there are 3, and then 6 valence electrons, of which there is 1. And now this has a positive charge. So I'm going to subtract 1 because of that positive charge. Okay, so then the total number of electrons is 8 divided by 2. That's 4 pair. The least electronegative element goes in the middle, but never hydrogen. Therefore, consequently, that oxygen goes in the middle. Then we have 3 o'clock, we have 6 o'clock, and we have 9 o'clock. And then we have 4 pairs of electrons. That's 1, 2, 3. Don't put lone pairs on any of those hydrogens. Don't double bond those hydrogens. Did you hear that? don't do that. So the next rule is to put lone pairs of electrons on that central atom. And since this is an ion of a charge here, we are going to put that in brackets with that charge right there like that, plus. Don't forget about those brackets for any charged species. Okay, that X geometry is A for that oxygen, X for each of the hydrogens, that's 3, and E for this lone pair of electrons on that central atom. Do you notice that I did not include an E for any of these lone pairs? Why not? Because these lone pairs are not on the central atom. These lone pairs are not on the central atom, so I did not include that in the X. It's only the lone pairs on the central atom that are included in the X. This is trigonal pyramidal. Which has a bond angle of 107. And its hybridization is sp1, p2, p3. That's sp1, p2, p3. So that's sp3 hybridized. And that looks just like this. It looks very similar to what we have done before. Any trigonal pyramidal structure looks the same. Okay, trigonal pyramidal, the same. And all trigonal pyramidal structures are polar. That's a for sure thing, an absolute. All right. Let's see if we can do the next one here. Okay. All right, so let's continue here. Let's gonna do the next one here. And the next one is chloromethane. Okay, chloromethane. So we've got carbon that has 4 valence electrons. There's one of those. So we've got hydrogen, that's 1 valence electron, of which there are 3 of those. And chlorine that has 7 valence electrons, which there is 1 of those. And that's 14 electrons divided by 2, because the crazy hat chemist can't count and can't handle big numbers, really is the problem. So I got 7 pairs of electrons. Okay, again, the least electronegative element goes in the middle, but never hydrogen. So here's another really big hint, and that is the halogens. And what we're going to do is we are going to color the halogens in pink today. I don't know why, but here are the halogens. Do the halogens go in the middle as the central element? More than likely not, unless you don't have any other choice but to go from one halogen to another. Okay, then that's what you got to do. That is what it is. So they are very electronegative. Okay, chloromethane. So it's not hydrogen and it's not going to be the chlorine because that's a halogen. So it must be the carbon. So the carbon is king that goes in the middle. Now you are doing that plus sign, 3 o'clock, sign of the cross, 3 o'clock, 6 o'clock, 9 o'clock, high noon. It doesn't matter where you put the chlorine, where you put the hydrogens. I'm going to put the chlorine off to the right, but it does not matter. So I got a hydrogen here, a hydrogen here, and a hydrogen here, and that would be. All right, so that again is I put the chlorine here and the hydrogen, hydrogen, hydrogen at 3, 6, 9, and 12 o'clock. And just to make sure, we could have placed this chlorine at any one of the locations of 3, 6, 9, 6, 9, or 12 o'clock, and it would not make any difference whatsoever. Okay, just making sure. All right, so here we go. Let's continue on with this and see what we got. We got 7 pairs of electrons. Our first rule is put a pair of electrons between the central and outside, central and outside, central and outside, central and outside. Okay, then lone pairs on the outside elements. Do I do this? Heck no, I just violated the duet rule. Boop, boop, boop. Can't do that. Nope, gotta erase that. Okay, all right, so what do? You got 4 pairs that you have used. You got 3 more pairs yet remaining. That carbon has an octet. The hydrogens have a duet. That chlorine is lacking an octet, and that's where those 3 pairs of electrons come in. That's why you're following the set of rules. I cannot emphasize this enough. What you really need is you really need to be following these rules in order. There is a specific order that I have written these rules down. You need to be following these rules. If you are not following these rules, you are not going to get the correct answer. Okay, all right. You're going to verify the octet rule for chlorine. For carbon, and that's correct. And hydrogen for the duet rule, that's good to go too. This is A for the central carbon. That's X for the three hydrogens and the chlorine. So that's AX4. Okay, it doesn't distinguish. That X can be anything attached to the central element. So that's perfectly fine. So this is tetrahedral. And that has bond angle of 109.5. And this is sp1, p2, p3 hybridized. That's sp1, p2, p3 hybridized. That's sp3 hybridized. All right, fantastic. And then you need to build yourself a model to figure out if it's polar or nonpolar. And check that out. That green thing is a chlorine, and I'm going to turn this here so you can see it. It is a tetrahedral arrangement of electron domains. Okay, and does it have bond polarity? Yes, it most certainly does. And it doesn't have a molecular polarity. Is it asymmetric? Yes, it most certainly is. That molecular polarity would be pointing in the same direction as my pencil. So this is most certainly polar. Party on, Garth. That's right, folks. All right. So now we're doing the next one right over here, and I'm going to scroll this up, and hopefully you do remember what's on the top of here, but we do need to scroll this on up here. Okay, so we're going to scroll this on up so that we got it all. And I think that would give us what we need. Oh, just a little bit of advertising gimmick here of, hey, I am the crazy hat chemist, and I am crazy, and I do wear hats on Fridays, and I am a chemist. So I think that all goes very nicely together. This next one here is carbon dioxide. Carbon dioxide. Carbon has 4 valence electrons. There is 1 of those. Oxygen has 6 valence electrons. There are 2 of those. So for a total of that 16 electrons, divide by 2, because a crazy hat chemist can't handle big numbers. So that would be 8 pairs of electrons. Okay. Now, I'm going to draw this in a particular way, and you could draw it in any way you want to. You can draw it at 3 and 6 o'clock, but I'm going to draw it in a particular way because I already know the shape of which this is already. So hopefully you're okay with that. Carbon is king. It's going to go in the middle, the oxygen on the outside right here, and another one on the outside here. The first rule is to place a pair of electrons between the central and the outside. I'm going to use my pencil now, and I highly recommend doing these in pencil with an eraser so that you can make changes as is necessary until you know what you're doing. Okay, so the next rule is place lone pairs of electrons on the outside elements. That's 1, 2. This is 3, 4, 5, 6, 7, and then finally 8. All right, this oxygen has 8 electrons. This oxygen has 8 electrons. This carbon is lacking an octet. And again, just to verify, there's carbon, nitrogen, oxygen, and fluorine. These 4 elements must have an octet. There are no exceptions to that rule. All right. So now what we got here is that we are going to, yes, well, what we have to do is sharing is caring. So what we're going to do is we're going to bring in this pair of electrons and bring that in and form a double bond. Now, that carbon has 6 electrons instead of the 4 in which it has. That's getting closer to the octet. We're going to take this pair of electrons and then bring that in, and that will form a double bond here like that. So what do we have yet remaining? We have effectively here, let's see if we can draw these here that have not been moved and then erase everything that has been moved. And then you can see what we've got. There we go. There is our carbon dioxide. You can clearly see that this oxygen on the right-hand side has an octet. That's 2, 4, 6, and 8. This oxygen on the left-hand side, 2, 4, 6, and 8. And that carbon in the center, 2, 4, 6, and 8. All right, perfect. The axe-like geometry here is A for the carbon and X, and there are 2 oxygens. This is linear. And that is SP hybridized, just SP hybridized. If it's linear, it has a bond angle of 180 degrees. And that's what we got so far. So there we go. We're going to answer this next question in just a moment. All right, now the next thing you need to do is build that model. Here's that model, folks. Okay, now you're seeing a double bond here. That's the carbon, that's an oxygen, that's an oxygen, and there's the double bonds. I don't have the lone pairs written down there for the oxygens, but hopefully that's okay. That is most certainly linear. Does it have bond polarity? Yes, it does. That bond polarity is going away from the carbon towards the oxygen, away from the carbon towards the oxygen, but they're pulling away from each other in equal amounts. That makes it symmetrical, and this would be non-polar. All right, fantastic. Let's put that off to the side, and we've got that one nailed. All right, next one is BF3. That is boron trifluoride. As a binary non-metal compound, boron has how many valence electrons? 3. There is rather 1 boron, and fluorine has 7 valence electrons, of which there are 3 of those. So that's 24 electrons. Divide by 2, that's 12 pair. All right, here we go. Boron, a fluorine, a fluorine, a fluorine. Now, by the way, I did figure out that the least electronegative element goes in the middle, but what is the most electronegative element? That's right, folks. Say it out loud. 1, 2, 3, say it out loud. What's the most electronegative element? That would be fluorine. So does fluorine go in the middle? Heck no. No way. All right. So now to place those electrons around it. First, bonding pairs of electrons between the central and the outside element. Perfect. Then lone pairs on the outside. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and finally 12. Okay. And then what we do is we circle these. So I'm going to circle this. Does it have an octet? Yeah. Does it have an octet? Yeah. Does it have an octet? And oh, by the way, just to verify, does fluorine need an octet? Yes, it's in this rectangular purple box. There are 4 elements that must have an octet: carbon, nitrogen, oxygen, and fluorine. So heck yeah, it needs an octet. How about that boron? Does that boron have an octet? No. Oh, so what are you going to do? Should you take away some of these electrons over here and form a double bond? Huh. Sounds like a good idea. That gives me the boron of having an octet. But there is an important rule, and that rule is right here. Check for exceptions to the octet rule. That is, boron and beryllium can be electron deficient. That is less than an octet, and that is acceptable. So, do you double bond a halogen like that? No way. Never, ever, ever do you double bond a halogen. Period. If you double bond a halogen, I'm going to come over and throw a molecule at you or something like that. Okay? So don't double bond a halogen. Fluorine, chlorine, bromine, iodine, those are halogens. Do not double bond them under any circumstance. It is one of the common mistakes. All right? This has an A, an X, and a 3. This is trigonal, planar. This has a bond angle of 120 degrees. It is sp1, p2 hybridized. That's sp2 hybridized. Build the model. That's what the model looks like right there. It's trigonal planar. That is the coolest thing right there. Snap. Okay, it's trigonal and it's planar. All the atoms are in the same plane. Does it have bond polarity? Yes, the bond polarity is going from that boron to the fluorine, from the boron to the fluorine, from the boron to the fluorine, but it's symmetrical. So that means that this is non-polar. Booyah! All right, so we are done with the front and back of the first page. We have more pages to go through, so let's see if we can plow on through to the next. All right. Here we go. Let's see here. Here we go. Let's keep on going. Getting a little bit tired, but don't stop, baby. Don't stop. This next one here is molecular oxygen. I think I forgot to write down molecular nitrogen when we came across that, but that was on the front page. I do apologize for that. You can go back to that. Oxygen has 6 valence electrons, of which there are 2. That's a total of 12. Divide that by 2, and I get 6 pair. So here we go. That's an oxygen and an oxygen. First rule, placing electrons, bonding pair of electrons, and then I am going to do, that's 1, 2, 3, 4, 5, and 6. Well, this oxygen here clearly has 8. That's 2, 4, 6, 8. This oxygen here on the left-hand side has 2, 4, 6. So it is not having an octet. So what you're going to do is you're going to erase these 2 electrons right here. Sharing is caring, and you're going to form a double bond. That will be what you're looking for. And then you will get the following structure. And then let me erase what I need to erase here. Boom. Now you can see molecular oxygen, okay? Just like before, when there's not 3 atoms, there is no shape, okay? And then there's no bond angle, so Na on that one. And this is the same as far as its electronegativity, so that means that this is non-polar because it fails on the first rule of polarity. Hybridization, sp1p2. Let's try that again, sp1p2. That's sp2 hybridized. All right, cool. Now, oh, you should see that when I did sp1p2 hybridize, that double bond counted as one region, and that's perfectly fine. There's nothing wrong with that. All right. Let's do the next one here, and that is phosphorus pentachloride. Pentachloride. Okay. So phosphorus has 5 valence electrons. Of course, there is 1 of those, and then chlorine has 7 valence electrons, and of course, there's 5 of those, and we're going to add those up, and we get 40 electrons. We're going to divide by 2. That's 20 pairs that we are going to be working with. Now that we got that 20 pair that we're working with, we're going to find the least electronegative element. That's going to be the one that's going in the middle. That is furthest from the fluorine. So what's farther from fluorine, phosphorus or chlorine? Most certainly the phosphorus is farther from the chlorine. Now, I'm going to do X marks the spot, the sign of the cross, 3 o'clock, 6 o'clock, 9 o'clock, 12 o'clock. But now you should see that you have 5 chlorines, and you're going to ask yourself, is there another rule I need to be considering? Because you are going to exceed the octet rule. And then you're going to ask yourself the following. Here we go. Period 3 and greater, that's periods 3, 4, 5, 6, and 7, can have greater than an octet. They can exceed the octet rule. And that is okay. By the way, I have already mentioned this, that is carbon, nitrogen, oxygen, and fluorine must obey the octet rule in all circumstances. Have done that many times, mentioned it, didn't highlight it. So the question is phosphorus in period 3 or greater? So we're going to put our periods here on our periodic table. Periodically, that's helpful. Period 1, period 2, period 3, period 4, period 5, period 6, and period 7. So is phosphorus in period 3 or greater? Yes, it is. It is in period 3. That means that phosphorus can exceed the octet rule. So that means that I can place greater than an octet around the phosphorus. So I'm going to place the chlorine here, chlorine here, chlorine here, chlorine here, and a chlorine here. All the chlorines are going to be around that phosphorus, just like such. First rule, bonding pair of electrons between the central and outside, central and outside, central and outside, central and outside. That's 5 of my 20 pairs. So that's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and finally 20. Whew. Now circling each chlorine, does it have an octet? It must have an octet. Yes, it does. Circling that phosphorus, does it have at least an octet? Yes, it does. Has it exceeded it? Yes, it is, because it's period 3, and that is okay. No problem. This is A for that central phosphorus, X for each of the chlorines, of which there are 5. So that means that this is trigonal bipyramidal. And there are a set of bond angles when it's trigonal bipyramidal, and that is going to be 120 degrees and 90, the combination of both of those. The hybridization of this is going to be follows. S, P1, P2, P3, D. That's, again, we can start anywhere. S, P1, P2, P3, D. That's S, P3, D1, or just D hybridized. Then what you're going to do is you're going to build that molecule, and here is that molecule. Let's check this out. So in the plane is a trigonal structure. So my all my fingers are touching the trigonal structure, and that's trigonal bipyramidal. So let's turn this, and then you can see that it is a bipyramid. There's a pyramid right here, and there's a pyramid right there. Has 5 domains. So the bond angles within the plane of that trigonal structure is 120, and then here is 90. So you should see that this 90 is right here, and then this is that 120 right there, 120. And it looks very similar in the central area, just like this trigonal planar structure, except it's not planar. It's bipyramidal. Okay. The 5-domain structure, has it exceeded the octet rule? Oh, most certainly it has. Is this a symmetric? Is this a symmetric? Does it have polar bonds? Yes. Is it a symmetrical molecule? Yes, it is. So that means it's no party, non-polar. Sorry about that. Okay, our next one here is carbon disulfide. And that is C for 4 valence electrons, of which there is 1, and sulfur, that's 6 valence electrons, of which there are 2 of those. So that's a total of 16 electrons, divide by 2, and I got 8 pair. The least electronegative element goes in the middle, that is carbon. And it just so happens that carbon and sulfur have the same value of electronegativity of 2.5. However, so let's check this out. Carbon and sulfur have the same value of electronegativity. And I don't know if you knew that or not, but carbon and sulfur have the same value of electronegativity. But if you look at the distance between carbon and fluorine and carbon and sulfur, you can clearly see that carbon is farther away. So because of that, carbon is going to go in the middle. So that is carbon in the middle, and then these sulfurs are going to go outside of that. And again, I've drawn it in a particular way because I already know the shape. So this will be the following. First is bonding pair of electrons between the central and the outside element like that. So that's 1, 2, 3, 4, 5, 6, 7, and 8. We are following the rules. When we place these electrons here, we are following the rules of which are outlined here very specifically. Okay, and those rules are placing a pair of electrons between the central and the outside element, placing those electrons on the outside elements, and then dumping the remaining electrons on the center element. Remember, there is no ownership to electrons. In fact, that is highlighted here. There is no ownership to electrons. Follow the rules for placement. That's why I have written it in this way. There is no ownership to electrons. Don't think like, oh, nitrogen has 5 electrons. You need to have 5 dots around it. Don't do that. Don't think about that. That doesn't work that way. Okay. So throw that away. That's middle school stuff. Don't do that. Bad. Okay. So here we go. That each of these sulfurs has an octet, and that is essential, but that carbon is lacking an octet. So that means that we are going to beg and borrow, and we're going to erase these pair of electrons right here, and we're going to get ourselves a double bond. We're going to erase these pair of electrons here and get ourselves a double bond, and then that would have an octet for both the sulfur and the carbon then at that point in time. So I'm going to erase all that pencil mark stuff, and then you can see the final Lewis dot structure correctly done, just like that. Beautiful, looking like a beautiful thing there. A is that central carbon. X are each of the sulfurs. There are 2 of them. This is linear. This is sp hybridized, sp hybridized. If it's linear, it has a bond angle of 180 degrees. And you're going to build the model, and that's what it looks like right there for that linear-like structure that's sp hybridized. And so is it polar or non-polar? Well, it actually fails in the first category of polarity, which is, does it have polar bonds? And that is, there is no difference in electronegativity between the carbon and the sulfur. So it's non-polar. However, if you didn't get that one, then this is a symmetrical molecule, and then it fails that one as well. So it's nonpolar because it's symmetrical, and it fails both the symmetry and bond polarity. All right. The next one, dihydrogen sulfide. Cool. So valence electrons 1, there is 2 of these hydrogens. Valence electrons 6, and there's 1 of those sulfurs. That's 8 electrons. Divide by 2, that's 4 pair. The least electronegative, but never hydrogen, goes in the middle. So that sulfur goes in the middle. There's a hydrogen here, just like that. Bonding pairs of electrons first, just like that. We cannot put any more electrons around the hydrogen because it follows the duet rule. So don't even think about doing anything more. Next rule, lone pairs of electrons on that sulfur. That goes just like that. That is a thing of beauty. This is A for that central sulfur, X for the 2 hydrogens, and E for that 1, 2 lone pairs. That is bent or angular. You only need one of these words. It's either bent or angular. You don't need both of those. It is sp1, p2, p3 hybridized. That's sp3 hybridized. If it's bent or angular, it has a bond angle of 105 degrees. And you're going to make that structure. We've made this before. It's the same one with the water, except for this time we have a sulfur in the middle instead of that red one. It's going to be a sulfur. And that is most certainly bond polarity, yes, and asymmetry, yes. So this is polar. Oh, yeah, baby. Perfect. All right, so we're going to scroll this on up here, and we're going to do the next one here. Our next one here is sulfur hexafluoride. Excuse me, not sulfur hexafluoride, it's sulfur tetrafluoride. Question is, who of you actually caught that? I wonder if anybody caught that. Sulfur tetrafluoride. So sulfur has 6 valence electrons, of which there is 1 of these babies. Fluorine has 7 valence electrons, of which there are 4. And so that's a total of 34 electrons. Divide by 2, that's 17 pair. The least electronegative goes in the middle. That's going to not be the fluorine. That's going to be the sulfur. And then the fluorines are going to surround it. Here we go. There's 1, there's 2, there's 3, and there's 4, just like we've always been doing. First rule, 1, 2, 3, 4 bonding pairs of electrons first. Then lone pairs of electrons on the outside elements. So we've done 1, 2, 3, and 4. That's 5, that's 6, that's 7, that's 8, that's 9 and 10 and 11 and 12 and 13 and 14 and 15 and 16 and oh, I have one more pair for 17. Where do I put them? Well, that's why we follow these rules to the T. That is, we first place pair of electrons between the central and outside, then on the outside elements, and then finally dump the rest on the central element. So that is just like that. I'm going to highlight this here. That is a lone pair of electrons on the central element right there. This is going to be AX4E. Okay, AX4E. That is called disphonoidal or seesaw. You know, like a seesaw when you're at the playground, a seesaw. And this is SP1, P2, P3D. This is SP3D. Let me do that again. Lone pair S, P1, P2, P3, and D. Okay. So disphonoidal seesaw has bond angles that are less than 120 and less than 90 most commonly. This is an asymmetrical molecule that has polar bonds, and this is polar, but we need to actually make that structure. So here is that structure. It is the trigonal bipyramidal basic shape, but this lone pair of electrons needs as much space as possible. Where is there more space? In the plane of 120 or at the poles of 90? In the plane of 120. So that's why it goes here. And this is why it looks like a seesaw. So hopefully you can see that. There's the seesaw. There's the seesaw, just like that. And this is asymmetrical, most certainly. Okay. Disphenoidal or seesaw. Okay. That's what you got for that one. All right. Oh my gosh, we just finished another half a page, or way the whole entire side of this page. Now what we need to do is flip this over and do the back side of this page. Whew. All right, here we go. All right, so this next one over here, where you're going to do the back side of this page, this next one is chlorine trifluoride, and I actually have the name actually written down there on there for you. And that is because I've discovered that some students didn't think that that was a chlorine, and they thought it was a carbon, an iodine, and a fluorine, of which it is not. So there's a chlorine has 7 valence electrons, of which there is 1. And there's a fluorine with 7 valence electrons, of which there are 3. So that's really 7 times 4, that's 28. And divide by 2, that's 14 pair. The least electronegative element goes in the middle. Fluorine is the most electronegative element, so it has to be that chlorine, just like that. Then 1 fluorine, 2 fluorine, and 3 fluorines, just in that same 3, 6, 9 o'clock positions, like the sign of the cross as well. Okay, and we have 14 pairs. First rule is bonding pairs of electrons between the central and the outside elements. That's 3 of those pairs. Then lone pairs on the outside elements. So that's 3, that's 4, that's 5, that's 6, 7, 8, 9, 10, 11, 12, 13, 14. I have 2 more pair. The next rule is to place them on the central atom here. Okay, I'm going to highlight these 2 lone pairs of electrons on the central atom, just like that. Perfect. Oh, by the way, these fluorines have an octet. That chlorine has an octet, and it has exceeded the octet rule. But that's okay, because chlorine is period 3. In fact, if you were to look at the previous page, that sulfur is actually period 3, and that's why it was able to exceed the octet rule again. That's okay. So this is A for that chlorine, X3 for the 3 fluorines, and E2 for each of the lone pairs on the central atom. And this is called T-shaped. T-shaped has bond angles that are 180 and 90. Okay. The hybridization is such that it is S, a P. S, P1, P2, P3, D. It's S, P3, D hybridized. Let's do that again. We can start anywhere we want. S, P1, P2, P3, D hybridized. And let's make that model for our polarity. So here it is. Again, the lone pairs of electrons go in the central trigonal planar domain because that's where there is more bond angle to have, if you will. There we go. And that's why it looks like that. And you can see there is the Mr. T shaped. Oh, I pity the fool. I'm Mr. T. Who. All right. By the way, this is asymmetrical and this is polar. Anybody get that joke? Okay. All right, good. All right. Next one is xenon difluoride. All right, and so xenon has 8 electrons, of which there is 1, and fluorine has 7 electrons, valence electrons, of which there are 2, so that's a total of 22. Divide by 2, I get 11 pair. Woohoo! Yeah, baby. What is the least electronegative element? Well, it's certainly not that fluorine. It's certainly the xenon. So the fluorines go on the outside of that. So placing these electrons, as always, we are following these rules. Bonding pairs of electrons between central and outside element. And then we have lone pairs. So that's 1, 2, 3, 4, 5, 6, 7, and 8. 9, 10, and 11. So we have 3 more pair to do. That's one, and here's two, and there's three paired. Notice that I'm dumping them all in the central element. Nothing wrong with that. That's what we're supposed to do. That's what the rules tell us to do, in fact. So this is A for that central xenon, X for each of the two fluorines, and E for all three lone pairs of electrons on that central atom. Booyah. And then hybridization is S, P1, P2, P3D. That's sp3D hybridized. Oh, by the way, AX2E3 is linear. And that has a bond angle of 180 if it's linear, like duh, of course. And then here is our structure. Notice that there are three sets of lone pairs of electrons on that central atom, just like that. And that makes this symmetrical. Even though it has bond polarity, it does not have molecular polarity. So this is no party, man. No party. Sorry, Charlie. No party. All right. Move that off to the side. We're going to do our next one here. And yeah, I think we can keep this here. This is sulfur hexafluoride. Hexafluoride. Whew, let's see here. This is 6 valence electrons. This is 7 valence electrons. There's one of these sulfurs and 6 of those fluorines. That's a total of 48. Divide by 2, that's 24 pair. The least electronegative element goes in the middle. That's the sulfur. Then that sulfur, is it period 3 or greater? Because we are going to exceed that octet rule just like we did with that xenon, because xenon is actually in period 5. Can it exceed the octet rule? Oh, heck yeah, baby. Oh, yeah. So we're going to place 6 fluorines around this, and we're going to equally space out those fluorines around that sulfur because it can exceed the octet rule. So here we go. 24 pair. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Oh my gosh, I think I made it. Probably I should have done this one over here like that. I was just worried about the confining everything, cramping it all in. All right. Sulfur exceeded the octet rule, and that's totally chill for sulfur. Boom, done. A for that central sulfur, X for each of the fluorines, of which there are 6. This is octahedral. And everybody's confused about this octahedral shape thing, and I'll show this in just a second. This is SP1, P2, P3, D1, D2. That's SP3, D2. That's as good as it gets, by the way. This has bond angles of 90 degrees since it's octahedral. And now what you need to do is build it and they will come. And here it is. There it is. Octahedral. Check this baby out. This is a beautiful thing. Thing of beauty. Check it out. Oh, yeah. I love it. It twirls. It twirls. It's octahedral. It's a square in the middle and it has, wait, octa and there are 6. What's wrong with that? Really? It is octahedral because it has 8 sides to it. That's why it's octahedral for 8 sides. And it is non-polar because it is most certainly symmetrical. Even though it has polar bonds, it's symmetrical. All right, we are going to continue on here. I am not done. I still have some voice left in me. I know you're probably disappointed about that, but here we go. We're going to move this on up. Click, 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 click. All right, there we go. We got 2 more to do on this side, and that's bromine pentafluoride. Bromine pentafluoride, so that has 7 valence electrons. That has 7 valence electrons. There are 5 of these and 1 of those. So it's really 7 times 7 times 6, which is 42 divided by 2, and that's 21 pair. The least electronegative goes in the middle, and that is certainly not the fluorine. So that's that bromine. So here we go. 1, 2, 3, 4, and 5 fluorines. We got 21 pair. That's 1, a 2, a 3, a 4, a 5. Is bromine period 3 or greater? Yes, it exceeded the octet rule. Okay, cool. That's 5. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Where are you going to go? You are going to go right here and a lone pair on the central atom. Good job. You did it. Congratulations. Okay. So that is AX5 for each, so A for that bromine, X for each of the fluorines, and then an E for that lone pair on the central atom, and that is S, P1, P2, P3, D1, D2. That is sp3d2 hybridized, and that is a shape AX5E, corresponds to square pyramidal. And this has bond angles that are less than 90 degrees because of that lone pair on the central atom. So there we go. There is square pyramidal. So you can see there's a square. There's a square. That looks like a square to you. That looks like a square to me. And it's a pyramid. No way, because it's three-dimensional, that lone pair. And this is most certainly asymmetrical. Totally, man, asymmetrical. That means it's polar, baby. Party on, Garth. Party on. Woohoo! All right, we got one more to do on this side of the page, and then we're done with this side. So this is xenon hexafluoride. Wait, what? Xenon, not hexafluoride, tetrafluoride. All right. So this is 8 electrons, and this is 7 valence electrons. There's 1 of these and 4 of these. So that gives us a total of 36. 36 divided by 2, that's 18 pair. Xenon, obviously, the least electronegative goes in the middle. And then I've got some fluorines. There's 1, there's 2, there's 3, and there's a 4. 18 pairs. So that's 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, 10, 11, 12, 13, 14, 15, and finally 16. Wait, 16. I got 18. 17 and 18. Oh, yeah, central atom. Xenon is period 3 or greater. Can it exceed the octet rule? Oh, most certainly it can. So that is AX. The A is for that xenon. The X are for each of the 4 fluorines. And then E2 for the 2 sets of lone pairs of electrons. This is square. Hopefully you're not square, or maybe it's okay to be square. Planar. And this has bond angles of 90 degrees. And it is SP1, P2, P3, D1, D2. This is SP3, D2 hybridized. Let's take a look at this model. Here it is. That's square. And oh yeah, all the fluorines are in the same plane. And someone's going to ask me, well, Mr. Crazy Hat Chemist, why didn't you put one of these lone pairs right next to each other? That's because lone pairs use up lots of space. They need lots of space, so that's why they're not right next to each other. That's why they're opposite. And that's why this is symmetrical. So this is no party, man. No party, non-polar. Dang. All right. Hopefully that's looking okie dokie for you. We have one more side here to go, and then we are going to be rocking and rolling here. Okay, so this one here, we actually have to spread this one out a little bit more because there's more that we need to do on each of these. So I need a little bit more space here to do all of these. So let's see if we can get this in like I want. All right, that is going to be much better. All right, so that's looking good. We are on the back page here. Okay, folks, I think you might actually be able to do this because we are on the final back page. So I know you've been waiting all day for this. I'm sure you have. So let's see if we can nail this down here. Let's see, let's get this straight. Okay, all right, here we go. So this first one over here is C2H2Cl2, and that's 4 and there's two of these, and there's one, and there's two of these, and there's seven, and there's two of these. That's a total of 24 electrons. Divide by 2, that would be 12 pair. Okay, fantastic. This is C2H2Cl2. So this is dichloroethene. And let's see if I have enough space for that. Depending on the structure in which we draw, then that name is going to slightly change just a little bit, but the name itself is dichloroethene. Still trying to get my zoom in here. Perfect. All right. Dichloroethene. Well beyond the scope of this class. That's an organic compound, so no worries about that. Okay, so there's a number of problems with this one. Well, no, there are no problems per se. It's just that there's a number of issues with this one. And this is the first structure that many students come up with. And I'm going to write this down here, and then you're going to find out that this is wrong and it doesn't make sense. So you got a you got a carbon in the middle. The least electronegative is in the middle. You got a chlorine, you got a chlorine, you got a hydrogen, you got a hydrogen. Oh, wait, you actually have another carbon. So can you do this? There's certainly enough electrons to do that, but you realize that carbon is one of those four elements that must obey the octet rule. It is not period 3 or greater. It cannot exceed the octet rule. So that means that would exceed the octet rule, and that is a violation of that. So this will not work. Okay. All right. So now we have to start looking at other things, and we have to start branching things off. So what we're going to do is we are going to go here, and then we're going to like put hydrogens and chlorines and chlorines and that kind of stuff. So let's see how this works and plays out. All right. So here we go. All right. So I already know what we're going to do. So what we're going to do is we're going to do the following right over here. And that is going to be a carbon and a carbon. All right. And then what we're going to do is we're going to place a hydrogen here and a hydrogen here and a chlorine here and a chlorine here. All right. This is what we'll do. We'll do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then wait for it. Wait for it. Here we go. 12. Those are my 12 pairs of electrons. And I'm actually going to zoom in on this, and so you can really see this. There's my 12 pairs of electrons, and that's what I have. But is that correct? The answer is no, because this right-hand carbon has an octet, but this left-hand one does not. So what we're going to do is we're going to erase this pair of electrons, and we're going to now make both carbons have an octet. And there we go. Now we've done it. So this is an organic compound. This is going to be carbon 1. This is carbon 2. Both of these are going to be structural centers. So really what is important is that you need to understand that we are really dealing with very small molecules to begin with. So I'm going to zoom on out here again, and then I'm going to put down this big gigantic thing here, which let's see if I can zoom on out a little bit more. And so we're going to zoom on out a little bit more just to show this. Okay. And let's pull this away. So this molecule right here. Okay. This is aspirin. Okay. So if you're getting a headache from watching my videos, give me a thumbs up and take some of this, because this is aspirin. And this is a much larger molecule than what we've been dealing with. And so one of the key components to this is that at each of these atoms, there is a shape. At each of these, there is a shape. And so we have been doing it in a very, very small way, and that we've been just looking at really, really tiny molecules where there's only a single central atom. For example, this is water. That red one, there's a single central atom. There's no like other atoms that could be the central atoms. Well, each of these black carbons and some of these red Oxygen's actually is a central atom. So actually at this here oxygen, this is bent. At this here carbon right here, this is trigonal planar. At this carbon, it's trigonal planar, trigonal planar, trigonal planar, trigonal planar, trigonal planar, trigonal planar, bent, trigonal planar, and tetrahedral. Okay, so I'm going to pull this one off to the side, aspirin, and hopefully you're not going to get a headache anymore by listening to my crazy hat videos. Oh my gosh, no way. So I'm going to pull this one away and we're going to continue on with our problem here. So pull away the aspirin. Hopefully you don't have that headache anymore now that I've taught you some more good stuff. All right, so here we go. Perfect. So that means that we have actually carbon 1 or carbon 2 that has each of these has their own individual shape. And so what we're going to do is we're going to write down these individual shapes. So at carbon 1, it's going to be A, X1, X2, X3. So A, X3. At carbon 2, that's A, X1, X2, X3. They're the same thing. And that corresponds to trigonal planar. And the hybridization of it is the same at each carbon. That is going to be sp1, p2 or sp1, p2. So it's the same hybridization, and that's sp2 hybridized. If it's sp2 hybridized, then the bond angle is 120 degrees. All right, now, everybody good on that? Give me a thumbs up. Give me a thumbs up on my YouTube channel. Give me a thumbs up on this video if you're good on that. Okay. All right. Then there's the molecular polarity. Okay, so what we need to do is build the molecule, and there we have it. Here is the molecule right there, just like that. So you should see that there's that double bond right here, right there. There's that double bond. These are single bonds. These black ones are the carbons. These green things are the chlorines. These white things are the hydrogens. Looking good so far. All right, and then we need to be thinking, well, chlorine is most certainly more electronegative. Bond polarity, carbon is more electronegative. Bond polarity, molecular polarity going in that direction. That means this is a polar molecule. So I'm going to pull that away. I'm going to zoom on out for just a little bit, and we're going to write P for polar for the molecular polarity of this dichloroethane. This happens to be 1,1-dichloroethene. Sorry, 1,1-dichloroethene. Okay, now there is one other thing here, and that is called an isomer. Does this have isomers? What are isomers? What are you talking about, crazy hat chemist? Isomers? You haven't mentioned anything like that before, unless, of course, you have actually watched the video on this lecture series first, of which I highly recommend that you watch the video on the lecture series first. Otherwise, none of this junk makes sense. Okay. So an isomer, these are called geometric isomers, geometric isomer structures. They are alternate Lewis structures where the physical arrangement of the atoms differs. So a thought. Here's my thought. Has anybody played with Mr. Potato Head before? Do you know Mr. Potato Head? Well, if you don't, then you should. So here is Mr. Potato Head. Wave to Mr. Potato Head. Well, there's Mr. Potato Head. Hello, everyone. I'm Mr. Potato Head. Sorry, I'm losing my tongue. So if you haven't played with Mr. Potato Head, and the reason why I mention this is that Mr. Potato Head is just like isomers. Isomers are the fact that, well, you know, I mean, maybe with Mr. Potato Head, you can take off his ear and then replace it with an arm. I mean, you would think that Mr. Potato Head shouldn't have two arms on the same side, so maybe we'll put an arm over here like this on his left-hand side, and then we'll put an ear down over here like that. So this is very similar to isomers. What you're going to do is the same Mr. Potato Head, it's just that you're going to take away parts of him and put them back in other places. So that is what an isomer is, a geometric isomer. There are different kinds of isomers, but for right now, we're talking about geometric isomers. So what we are going to do is look at this structure and then ask ourselves, can we pull off any of the atoms and change them into different locations? And most people get another isomeric structure. And so let's write that one down. So we're going to do a carbon, and then we are going to pull off one of these chlorines, and we're going to replace it with the other one. And so we're going to keep this chlorine right where it's at, and we're going to put the other one here and put the other hydrogen here and the other hydrogen here. And so this will be one of our isomeric structures. It's still going to have the double bond, single bonded for the oxygen, single bond for the chlorines, and 3 sets of lone pairs of electrons for the chlorines because it's a halogen and all halogens have 3 sets of lone pairs of electrons. So that is an alternate isomeric structure. So this is our first one. Let's put that one here. This is our second one. That one's right there. Do you see that these are actually different here? These are most certainly different. Okay, these are called cis-like structures. So this is cis, same side is cis 1,1 dichloroethene. And this one is cis, same side, 1,2 dichloroethene. Cool. And that one is also polar because it's asymmetrical. So I'm going to write down polar for both of those. I'm going to scratch out this polarity right here. Now, those are 2 of 3 structures. So we're going to do one more, and we are going to play Mr. Potato Head again, because everybody likes to play with Mr. Potato Head. And here is the third isomeric structure, and that is, I'm going to keep this chlorine right where it was before, but I'm going to put the other chlorine opposite of it. Okay, and then here are our bonds. Let's do this in red like we were doing. The chlorines have 3 sets of lone pairs of electrons like all halogens always do, and the hydrogens are just a duet rule like all halogens would. Okay, sweet. And that's what this one looks like here. This one right here is called trans 1,2-dichloroethene. Trans 1,2-dichloroethene. And trans is like a trans across transcontinental railroad. So that's across. That's why it's trans, because it's across. The railroad is cross on the other side. And cis means same side. Okay. So this one is the only one that is non-polar. So this is no party for this one because the bond polarities cancel them out. This is non-polar and these 2 are polar. You definitely need to know these. They all have the same shape. They all have the same bond angle. They all have the same hybridization. You need to know these 3 structures or ones like it because one of these is going to be on your quiz or test. Guaranteed. Did you get that? I'm sure you didn't, but maybe you did. All right, then what we're going to do is we're going to do this next structure. So we are going to slide this over one column here, and then we're going to see if we can do this next one. This next one also has the same pairs of electrons. That's 12. And we're going to do a similar type of structure here. It has these 2 carbons right here. We're going to do a hydrogen here, and then we're going to have this CH3 as a group. CH3 as a group. We're going to have this double bond, single bond, single bond, single bond, single bond, and this is also a dimethyl ethene. It's 1,1-diethyl ethene compound. It's actually probably a propane compound when it's correctly named, but that's okay. I'm just trying to get you to this simple point right here. It is also a X3 and it's trigonal, planar, trigonal, planar. It's also sp2 hybridized, 120-degree bond angles. This one here, how I have drawn it, is polar. That is, it's asymmetric. It's really not a polar structure because there's no difference in electronegativity, but That's besides the fact. Then the next one here is similar to what we did before too. And that is that these groups are here like this. Remember, this is Mr. Potato Head. Mr. Potato Head. Gotta love Mr. Potato Head. Slide this on over so that you can see the final Mr. Potato Head. Okay, and that would be here like this. And then since this is truly just a hydrocarbon, we would actually classify this as non-polar. This is a very special case, kind of outside of the box on all of these here, but hopefully you get the kind of basic concept here. We're going to have the CH3 group here, the CH3 group here, and the hydrogens here like this. Okay, this isn't going to be too much of a big deal one here for us. So I'm going to move on to the next one, which is going to be even more important than this last set. But you definitely need to know this top one right over here. Definitely know this dichloroethene example. You need to know that. That's very important. All right, now we're going to move on over to this next problem here. And this is going to be nitrate. Why do chemists like to work during the evening time? Well, because the nitrates are better than the day rates. Chemistry joke there. All right, so 5 and that's 6 times 3 times 1 and then plus 1. So that's a total of 24 electrons divided by 2. That's 12 pair. What we're going to do is we're going to do N right there, like that. We're going to do an oxygen. We're going to do an oxygen. We're going to do an oxygen. Notice that this is an ion, so we need these brackets around this and that 1 minus charge up there like that. We're going to do 1, a 2, a 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And then you're going to ask yourself, does nitrogen need an octet? Well, most certainly it does. It's in period 2. So that means that sharing is caring. We're going to erase this pair of electrons right here, and we're going to do a double bond there like that. Okay. All right. And then we're going to do the VSEPR geometry of this one here as well. Okay, and this is going to be an A and an X and a 3. That is trigonal planar. And what does that look like? Well, I built the model. There it is for you. Notice that there is a double bond on it, and these atoms are all in the same plane. This is trigonal planar. Boom, boom, boom. Beautiful thing that it is. Okay, and what is the hybridization? That's sp1, p2 hybridized. So let's zoom on out so that we get the rest of this here. This is sp2 hybridized. If it is sp2 hybridized and trigonal planar, the bond angles are 120 degrees. Okay, and this has molecular polarity is non-polar. Now, this molecule of nitrate has one more super special thing, and that it has what are called resonance structures. Resonance structures. So what are resonance structures? Now that we got this full thing on here. Resonance structures are the movement of the double bond. So I'm going to draw the 3 resonance structures that are here on this, and you should be able to see this. So I'm going to put this one here like this. That's that one. Now, if I rotate this, there's another one, and I rotate it, and here's another one. So let's draw these. The nitrogen is here. The oxygen is here. The oxygen is here. The oxygen is here. Okay. I drew the double bond on the left-hand side. Now I'm going to draw the double bond down below, and everything else is going to be the same. When it's a single bonded oxygen, there are 3 sets of lone pairs of electrons. When it is a double bonded oxygen, it has 2 pairs of lone electrons. This is brackets and a -1 charge. That's moving this double bond from this left-hand location to down below right there. And then there's one more rotation, and that will move it over to here. So let's draw this one in the resonance column here. Double bond here on the right side, single bond on the left and down below. 3 sets of lone pairs of electrons. This one has 2 sets of lone pairs of electrons, 3 sets of lone pairs of electrons, brackets, and a -1 charge. Perfecto. These are all nonpolar. Those are resonant structures. So a resonant structure has the movement of a double bond. So for your future references, not one of these structures is actually correct because this is our feeble attempt at drawing resonant structures. All right. We have two more sets of resonant structures to do. We have two more problems to do. We're going to slide this baby on up and we are going to do these next two problems. Let's do this first one right here first, and then we'll do that next one. Okay, I think we're getting there. We're getting closer. Okay, this is sulfur tri. Oh, by the way, that was nitrate, right? This is sulfur trioxide. Okay, so that's 6 valence electrons. That 6 valence electrons, that is multiplied by 3. This is multiplied by 1. We're going to add them up. I get 24 electrons. That's divided by 2. That's 12 pairs. I got sulfur. I got an oxygen, an oxygen, an oxygen. Okay, we got 12 pair. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and finally 12. And I'm hoping you're seeing what happens. What we're going to do is we're going to take this pair of electrons and move it right into here just like that. And that will erase this here. That will give me an octet on that sulfur. That sulfur most certainly needs an octet. Now, there are two more resonance structures, and we're going to draw them right here and right here. And they all have the same shape. We'll do the shape first. That's AX3. That's trigonal planar. That's sp2 hybridized. That's 120 degrees. And all these are non-polar. So we're going to draw the two other resonance structures. That's an S, an O, an O, an O. Okay, and that is, I'm going to move this double bond now down below. Okay, and it's very similar to what we did with nitrate. Just another practice problem for you to do. Okay. Next one and last one is the sulfur here. And this time we're going to have that double bond on the right-hand side and single bonds in the other two locations. When you have a single bonded oxygen, there will be 3 sets of lone pairs of electrons. When that double bonded oxygen, 2 sets of lone pairs of electrons. All right, and then theoretically, what you should be doing is putting brackets around all this with double-headed arrows in between all these structures. And that is what you should be doing with all the resonance structures, is putting double-headed arrows in between these structures. Okay, that lets you know that not one of these structures is actually correct. There are no double bonds and no single bonds on this structure of sulfur trioxide or nitrate ion. In fact, the bonds are about a bond and a third in energy and in length. All right, and that is the same structure that we did for the nitrate. It's the same kind of thing. That is the sulfur trioxide. We have one more problem to do, folks, and then we are done with this. And this is sulfur dioxide. By the way, you were watching The Crazy Hat Chemist, and we got one more problem to do. I am so excited. We are almost done. That is 6 valence electrons times 2. We're going to add those up. We get 18 electrons, and I'm going to divide by 2. So that's 9 pair. We can do this, folks. We can do this. We are almost there. Almost there. I know it. We can do it. Okay. Here we go. Here we go. Where are we going? I don't know where we're going. Here we go. Sulfur dioxide. There's a sulfur. There's an oxygen. There's an oxygen. We got 9 pairs. So it's 1, 2, 3, 4, 5, 6, 7, 8, and then finally 9. Okay. Sulfur dioxide. Does the right-hand oxygen have an octet? Yes. Does the left-hand oxygen have an octet? Yes. Does the central sulfur have an octet? No. Does it need an octet? Yes. You're going to take this pair of electrons that I drew in pencil and bring them over here like that, erase these, and now you have an octet on all atoms which require octets. There's also a resonance structure on this, so you're going to have to put double-headed arrows and the brackets around it, and we're going to do it right in this spot here. So that's a sulfur, it's an oxygen, and hopefully you get the hint as to what to do. We're going to have that double bond in the other location. We're going to have that lone pair still on that one. We're going to have two sets of lone pairs of electrons on this right-hand oxygen. That will give us an octet. And then we have three sets of lone pairs of electrons on this oxygen, and that gives us an octet. Yes, we're getting closer. This sulfur or this sulfur, it doesn't matter, is sp1p2 hybridized. sp2 hybridized. Okay. And then what is the shape? It is A, X1, X2, that's X2, E, E1. So AX2E1 is angular or bent. An angular or bent has a bond angle of 105 degrees. If it's angular or bent, it is actually asymmetric by definition, period. You should be, and that's polar, and you should be making that structure, and that's what it looks like. And I have drawn the two resonance structures herein. If you are going to be really, really particular, then this structure actually has two more resonance structures with the lone pair of electrons below instead of above, because this double bond inhibits the rotation around this sulfur and that oxygen, or this sulfur and that oxygen. But I would be perfectly fine and very happy if you were to actually draw these two resonance structures, and that would be a beautiful thing. So, in summary, I am the Crazy Hat Chemist, and I hope you are learning lots of cool things here from me. I've got lots of molecules here. So what I'm going to do is, before we totally end this video, what I'm going to do is give you just a summary of the molecules of which we've been covering here. So hopefully that will be helpful to you. So first one, this is linear. Linear. That is a symmetrical molecule. Next one. After that linear shape, okay, we have trigonal planar. There's trigonal planar. This is like a trigonal planar structure, but it is bent because it has a lone pair of electrons on it. If all these white things are the same, then it would be nonpolar. This one is always polar because it's asymmetric by definition. Boom. Then this covers, this covers two domains, and these are three domain structures. So two domain structure right here on the left, and the three domain structures right here on the right. Then what do we have? A four domain structure that's tetrahedral, that's right here. Underneath that, then we have, of course, a trigonal pyramidal shape. That's right here, like that. Then underneath that, then we have a bent-like structure, and that is here, right here. So you should see all three of these here. Okay, let me just tilt some of these. So we have bent on the far right with the red. We have trigonal pyramidal in the middle with the blue, and we have tetrahedral on the far left-hand side with the black. All right, those are our four domain structures. Our five domain structures, this is trigonal bipyramidal. Then we have disphenoidal or seesaw. I'm going to have to zoom on out so you can see this here. There's trigonal bipyramidal. This is right here, seesaw, disphenoidal. Then we have T-shaped right here. Do you see the T? See the T? And then we have linear. These are five domain structures right here. Five domain structures. Okay, cool. And then we have the six domain structures. So let's just spin these around just a little bit. This is trigonal bipyramidal. This is seesaw or disphenoidal. Seesaw, disphenoidal. Then we have T-shaped. This is T-shaped. Then we have linear, another linear, right? This linear is obviously different than this linear, okay? These two right here are asymmetric and always polar, okay? Peel these away. Now, what we have is an octahedral structure. Octahedral structure, then one lone pair on there, and that is square pyramidal, and then two lone pairs, that's square planar. So octahedral, look at the octahedral. Check that out. It's an awesome like structure. I love it. It's octahedral because there are 8 sides to it, not because there are 8 regions around it. This is square pyramidal because it has that lone pair of electrons. You can see that square structure and it's pyramidal, right? Square in the plane that I'm touching upon and then pyramidal. And then there's a square planar structure. This is the square planar structure. Do you see all the green things are in the same plane, right? All right, I don't know what kind of plane, a 747 or a giant Airbus. I'm not really sure. All right, and then some other ones that we've actually had here is this one right here. This is a trigonal planar structure, but has a double bond in it. Another one that we had was this linear structure. This is carbon dioxide or sulfur dioxide or dicarbon, carbon disulfide. And then we have these structures, and that is one here, and one here like this. These two are cis ene structures, and this is a trans structure. Trans, remember, it's trans like across. So that's why this is trans, this is across. This is cis, meaning same side, cis, meaning same side. The two on the top are polar. The one on the bottom is nonpolar. So these two, right, this one and this one and this one are the cis, same side. These two here are polar, and this one is nonpolar. Okay. And then there are some other structures here. So if we have, starting with that methane, we're going to replace one of those hydrogens with the chlorine. That's chloromethane. That is polar, that is nonpolar. So methane is nonpolar. Chloromethane is polar. Dichloromethane is polar. Trichloromethane is polar. And like tetrachloromethane, which is called carbon tetrachloride, is nonpolar. Okay, so let me show you that these two on this top side right here are the two nonpolar structures, and then these three right here on the bottom here, these are the polar structures. These are asymmetric, these are symmetric. And of course, someone really wants to say hello to you, and that is Mr. Potato Head. He wants to say, thank you very much for watching. I greatly appreciate it. I am the Crazy Hat Chemist, and oh my God, he's wearing a hat and some sunglasses. So yes, of course, I'm wearing a hat too, and that's the Crazy Hat Chemist. And I hope you have a great day, and Cheerios. I'll see you next time for a great video. Hopefully you enjoyed this. I'll talk to you later. Bye for now.